So in this lesson, we're going to find the graphs of the other four trig functions: tangent, cotangent, secant, and cosecant. It's a one lesson topic. We don't do any transformations, but we just learn what the graphs look like. So to start out with, we're going to consider these rational expressions. It says what values of x are not in the domain of f of x equals 1 over x. So if I think about this, I can't divide by 0. So the number that's not in the domain, right, is 0. So x actually cannot equal 0. In this case, what number would make this denominator 0? So what number is not in the domain? That number is -2. Okay, so we're going to take the second one and we're going to sketch it on the graphing calculator. We're going to be answering some questions about the table and the graph, and then we'll come back to the notes. So I'm going to start out, just clear out my old graphs and go up here. I'm going to insert a fraction and type in 1 over x plus 2. Now, first thing we need to do is look at the table. That's the first question. So it says in your table what value of x gives you an error. So if I look through my table values, I should see that error at -2, which is what I was expecting from the last question. The next thing we're going to do is look at the graph. Remember, we have a pretty crazy window right now because we were doing trig graphs on the last problem. So I'm just going to press zoom 6. Remember, that brings me back to -10 by 10. So zoom 6. So here's my graph, and what we're seeing is what happens as we get closer to that value at -2. And actually, we're getting closer and closer to dividing by 0, which will give us positive infinity on one side and negative infinity on the other side. So what other function have we worked with that has this type of line where the graph can't cross? It's kind of for a different reason. It's not a rational expression, but if you remember your log graphs, they kind of made this pattern and they had a y value they couldn't cross or a vertical asymptote. So we're going to go back now and answer those questions. So on this graph, we'll quickly sketch it first. We don't see this line, but I'm going to draw in the vertical asymptote at -2, and this is just making sure we don't cross the line when we do the graph. So we have this one piece of the graph that's here, and we have another piece of the graph that's down here. So the value that gave us an error was -2. What is happening is you get closer to that value of x. The graph goes to positive or negative infinity. And lastly, what other type of function have we worked with that has a vertical asymptote? That's any log graph, so I'm just going to write log base b of x, or y equals log base b of x. So the reason we've been going over this seemingly unrelated topic, it says when a rational expression has a restricted value, its graph will have a vertical asymptote or a hole, but you don't have to worry about that in this course, so that's something else that can happen we're not talking about right now. We know that tangent of x, cotangent of x, secant of x, and cosecant of x can be written as rational expressions containing either sine or cosine. Therefore, these graphs have vertical asymptotes whenever their denominators equal 0. So we're going to start out and look at cosecant of theta and think about what's going to happen with that. First off, we need to think about the unit circle. Cosecant of theta is the reciprocal of sine. We know on the unit circle sine theta equals y. So cosecant of theta is going to equal 1 over y, and that's your rational expression. So we'll just label our basic 4 points. Okay, so when I do this 1 over y, if I talk about the cosecant of 0, there's my y value. That's 1 over 0, so that's undefined. The cosecant of pi over 2, we're going to use radians, which is 90, would be 1 over 1, which is 1. the cosecant of pi at 180 is 1 over 0. So again, we get undefined. And then if we continue around, cosecant of 3 pi over 2, right at 270, make that a little bit better, is 1 over negative 1. So that's negative 1. And lastly, if I come back up and do the cosecant of 2 pi, I should get the same thing as 0, which is undefined. So now we're going to work towards that graph of cosecant of theta. Now, since I kind of already went over this work on the other page, I'm just going to write it pretty quickly. This is what we did. So our angles were 0, pi over 2, pi, 3 pi over 2, and 2 pi. And remember, on the unit circle, we're following the values of 1 over y for cosecant of theta. So if you feel like you're good with this, you could, skip forward a little bit. So remember, we're dividing 1 by these values. 1 over 0 is undefined. 1 over 1 is 1. 1 over 0 again is undefined. And then 1 over negative 1 is negative 1, and 1 over 0 is undefined. As I said, I explained that a little more on the last page if you need to go back. So we're going to move down and start to look at a graph. So far, we've used the unit circle to find the trig values for the quadrantal angles. That's step 1. Now the next thing we're going to do is draw the vertical asymptotes. So anywhere I see undefined, I'm going to draw a dotted vertical line. We're going to plot the other points. In this case, we only have 2, and we're going to extend the pattern if the interval is larger than 0 to 2 pi. So we're going to have to go back to negative 2 pi. And then lastly, we have a couple different methods we can do to get the rest of the graph. So I'm going to try to leave both of these on here. So we'll start off with our axes. So we're going back to negative 2 pi. I'm kind of using that typical scale that I've used before. We have the pi over 2 and 3 pi over 2 in there. I'm not necessarily going to label it so this graph doesn't look too crowded for you. And pi there. Okay, so we're going to start out and do the asymptotes. So I have an asymptote at x equals 0. Remember, these are my x or theta values. So the graph does not cross this line. The graph does not cross here. And the graph does not cross here. Moving in the opposite direction, it's going to continue that same pattern. So I'm expecting one at negative pi and negative 2 pi if I went in the opposite direction. So next step is to put the points we know. So we know that at pi over 2, just put a little scale here, that's 1 and negative 1. At pi over 2, it's going to be at 1, okay? At 3 pi over 2, it's going to be at negative 1. So we want to think about this like bouncing up and down. 1, negative 1 will continue. So back at negative pi over 2, it's not going to be symmetric. It's just going to continue the up-down pattern. So it's going to be down here, not symmetric over the y-axis, I guess I should say. And then back up here, it's going to be back up here. And just a little more about that, if we're down at negative pi over 2, that should have the same value as 3 pi over 2. So we notice that these two values are the same. So now, how do we even connect these points? There's a bunch of points, high, low, there's lines we can't cross. So I'm going to talk about the ASTC first, and this is kind of the without the calculator method. Okay. So we're going to think about where these angles are. So from here to here, we're in the first quadrant. So that's where everything is positive. So this piece of the graph here, okay, has to either go to positive infinity or negative infinity. And since this is all positive, we're going to take the graph up to positive infinity. Okay, it has to either bend up or bend down based on what happens around vertical asymptotes. Moving on to the second quadrant, which would be values like from here to here, which corresponds to being here. We're in the second quadrant. Cosecant goes with sine, so that's also positive. So during these values, I'm also going to go up positive as I head towards the asymptote. In the next quadrant, we are in here. We're in quadrant 3. Here, sine, which goes with cosecant, remember graphing cosecant, is negative. So my graph is actually going to bend down towards negative infinity. I'm going to keep it in that same blue color, though, so we can see it's all the same graph. And fourth quadrant, same thing. Sine is negative. So we're talking about the part of the graph that's here, fourth quadrant, right? So it's going to go down negative. So this is not, like, you can't graph these with parabolas, but they kind of look like repeating parabolas up and down. We have another one over here, and it's going to keep that up and down pattern. So these are going to go down. And this one is going to follow that same pattern and go up. Okay, make sure they don't touch those asymptote values as you go along. So now we're going to look at how you would do this graph on your calculator. It is a lot to think about ASTC and pretty conceptual. So I can graph on my calculator 1 over sine of x for cosecant of x. My window, we went from negative 2 pi to 2 pi. And I'm going to make my scale go by exactly the same thing, which is pi over 2. So it really matches my graph. Maybe I'm going to go from, I don't know, negative 10 to 10 is fine. I'll leave it at that. I might want to come in a little closer, but that's fine. So now if I press graph, making sure once again I'm in radian mode, just want to point that out, and I press graph, I'm going to see that cosecant graph. And I think I am going to change this to match our window. So we just had from negative 3 to 3 for our y's on our little graph. And now if I look at that graph, it really does look like it. Notice I don't see the asymptotes. If you graph this without knowing anything, your graph is probably going to be messed up because you'll cross over the asymptotes. You won't really know what's going on. But it does help you see if you're having trouble knowing if you need to go up or down on each piece. Looking at this graph can really help you make sure that that's correct. So now we're going to go back to answer questions about the graph. What is the y-intercept of cosecant of theta? Well, it doesn't look like there is one, right? It can't touch the y-axis. The domain is kind of tricky. Basically, we could write negative infinity to infinity. These little patterns would continue, but there's values it can't equal. So I'm actually going to write all reals, but values x can equal. Well, I see it can equal, right, negative 2 pi here, or negative pi, or 0, or pi, or 2 pi. And I'm just going to put a ... on each end of that list to show that that pattern would continue. 3 pi, 4 pi, and so on in both directions. What is the range? Range is also kind of weird. Probably the easiest way, it's kind of like we have this middle road in here that doesn't have any y values. So it goes from negative infinity up to negative 1. This is the y value, including that value. Or, and we can actually use this sign. I don't want to be confusing with this. I think we might use this once more. That means or. It's a union sign. 1 to infinity. So there's this piece and that piece. Name one interval over which cosecant of theta is increasing. I'm going to do this part here. It can be really any spot where it's increasing. So my graph is increasing from pi over 2 to pi. And I'm just going to use parentheses because we don't really include those. Plus, we really can't include pi because there is no value there. And just to keep this lesson a little bit shorter, I'm going to skip this last question. I do just want to talk about the fact that you can do transformations on these graphs. So these, we could identify these transformations on cosecant, but basically it's not something required in the course.